Today we are looking at something called the discriminant, and it is one small part of something you have already learned. Specifically, it's part of the quadratic formula. So if we have a quadratic equation, so equals 0, this is the whole quadratic formula. But there's a part of it that is special, and that is just the inside of that square root, b squared minus 4ac. Not the square root of that, not the opposite of b plus or minus that, just that inside part. Now, there are three things that can happen, as you've seen when you've used the quadratic formula to solve problems. You could get 0 inside there, so you end up with the opposite of b, whatever that number might be, plus or minus the square root of 0 over 2a. So what's the square root of 0, everybody? 0. So then if I take whatever this number is, opposite of b, plus 0, what do I have? I still have the opposite of b over 2a. And if I take the opposite of b minus 0, I still have exactly the same thing. So I only get one answer. If that thing I'm taking the square root of is 0, I only have one real solution. Now, another thing we've seen that sometimes happens is we start plugging into all of that, and we get the opposite of b plus or minus the square root of some positive number over 2a. So now we've got the square root of something positive. Maybe it comes out to be an integer, maybe it stays the square root, but we know that that means we have the opposite of b plus whatever that square root is over 2a, and we have the opposite of b minus the square root of whatever that is over whatever the denominator turns out to be when we plug in. If that square root is a positive thing, those are two different numbers, right? But they're still real because we're taking the square root of a positive. So sometimes we get two different real numbers. And the other thing that we have seen is that we can get the opposite of b plus or minus the square root of some negative number over 2a. And that means that we have the opposite of b over 2a plus or minus some square root over 2a, and then we have the I in there. And we know we have one answer with the plus in there and one answer with the minus in there. And they both have that imaginary part, right? We've seen that happen on some problems that we've solved. So that is the third thing that can happen. We can have two different complex numbers as our solution. Up to now, we've been saying because there are no real solutions, the parabola doesn't cross. We're now going to start saying, instead of no real solutions, we're going to start saying two complex solutions. So here's what I want you guys to do to help speed up the lesson. I'm going to divide you into three groups based on where you're sitting. Each of you will do your equation on your whiteboard first, and then share it with the others in the group. And then you'll pick one person to go put it on the board up at the back, so that that way everybody's doing one, and then we kind of compare notes on these. There are going to be three quadratics that I want you to solve. I want you to solve it with the whole quadratic formula. Then I want you to graph it on the calculator. So you're going to change the 0 to the y. And then looking at that graph like you've been doing, how many and what kind of solutions? Do you have two real solutions? Instead of no real solutions, do you have two complex solutions? Or does it just touch the x-axis once? Do you only have one real solution? So we can see what the graphs look like. We can see what happens with all of that. And then I want you to look back at the work. Is the discriminant positive? Was it negative? Or was it 0? What was going on? So we can make some of these connections. As you do these, I'd like you to first get everything over on the left, so that you'll end up with a positive x squared term in there. So we're going to do something like x squared plus 3x minus 2 is 0. And similarly, with these two, bring everything over on the left. When you put it into the calculator, you will, of course, change that 0 to a y. So let's put together what my different groups came up with for these three. So on the first one, when we plugged into the quadratic formula, we got -3 plus or minus the square root of, and then this became a 17. So not real nice numbers. It was irrational. -3 plus root 17 over 2, -3 minus root 17 over 2, but we had two real solutions. When we drew the graph, we got one with the vertex at -1.5, -4 1/4. The y-intercept, we simply plugged into this. If x was 0, letting the 0 now be a y would have to be a -2. And we got the calculator versions of this -3 plus and minus root 17 over 2 for these two x-intercepts, matching that we had two real solutions. The discriminant is just the inside of that square root, 9 plus 8. The discriminant equals 17. If you have homework sets that say, what is the value of the discriminant? Calculate the discriminant. You need to do b squared minus 4ac equals 9 plus 8 equals 17. That was positive. That inside is what matters. The discriminant was positive. We had two real solutions. Now, you're also going to have some where we ask you to graph these parabolas and ask you, is the discriminant positive, negative, or 0? You don't have to figure out that it's 17. You do your graph. Oh, it crossed twice. There are two real solutions. That means the discriminant was positive. So you're going to have some of those kinds of problems, not on today's set, but on future ones. Okay, for our second one, when we plugged in on that, we got 4 plus or minus the square root of 16 minus 36 when we did the b squared minus 4ac. So we have the square root of this negative thing, which means that we ended up with these complex numbers, 2/3 plus root 5 over 3i and 2/3 minus root 5 over 3i, two different complex numbers for our solutions. When we did the graph, it did not cross the x-axis at all because it had no real solutions, or now because it had two complex solutions. And we got the vertex at 2/3, 1 and 2/3. The y-intercept was 0, 3, because if we put a 0 in, 0 plus 3, that's going to be our y-intercept. If we said, what's the value of the discriminant? We do the b squared minus 4ac equals 16 minus 36 equals -20, and we'd say the discriminant equals -20. Because it is negative, no real solutions, which we now write as two complex solutions. If you didn't have to actually find it, if you were just doing the graph, you'd say, oh, since it doesn't cross at all, that means the discriminant would have been negative. The last one, x squared plus 6x plus 9 gives us -6 plus or minus the square root of 36 minus 36, so the square root of 0 over 2, which means -3. This one is sometimes called a double real root because I could have factored that as x plus 3 squared equals 0. X is -3 from the first parentheses, x is -3 from the second parentheses. That's why the name double real root that you saw on the earlier slide there. That means only one x-intercept, which means the vertex is right on the x-axis, -3, 0. We plug the 0 in for the x, and if it was now y equals that quadratic, we would have had that the y-intercept was 9. One real solution. The discriminant is 0 because the discriminant is just that inside part of the square root. Anybody with questions on those three? In summarizing what we've covered, the discriminant is just b squared minus 4ac. It is not the square root of b squared minus 4ac. It is just that inside little bit. And I'll scroll back up here in a moment, but let me get these things up here so that I can also do the related pictures. If we change that ax squared plus bx plus c equals 0 to an ax squared plus bx plus c equals y, and so in this case, if we have a single real number, it means that the vertex is on the x-axis. Any of these parabolas may open either up or down. So that one might have looked something like this. If just that inside part is a positive number, we're going to get something that crosses the x-axis twice. So that we've got these two x-intercepts in there. That would mean we have two different real numbers for our solutions. And if we get a negative number for that, for just the b squared minus 4ac part, that means it does not cross the x-axis at all. So maybe we have one that does something like that. And we have no x-intercepts, so then we start saying we have two complex solutions.